Okay, but before we get there, let me just, because I didn't really talk to you yesterday, let me review the definition of the derivative that we know so far is that limit, and we've been doing as h approaches 0, but we also saw it as the change of x approaches 0, of f of x plus h, x plus change in x rather, minus f of x all over change in x. That's the same, obviously, as the limit as h approaches 0 of f of x plus h minus f of x all over h. Just we made the change of x in place of the h. And I only write it that way because this first example is written with that notation. So this limit is giving us f prime of c. It's giving us the derivative at some point for some function. So from this expression, which is like after we've already plugged into the derivative, this is asking us to try to figure out at what c value are they looking for the derivative, and what is the function. And again, this, for some people, this is like all thinking based. There's not really much work I feel like I can show. Some people will undoubtedly have a better knack for this than other people. I actually just had an idea of what I could do for you. Oh, I like that one. I just don't like the way that she wrote it. Hold on. Let me find a good one. Okay. Here's my comparison. Thanks, Taylor. What's happening in the problem that we're looking at is essentially they're giving us this, and they're trying to get us to go backwards and tell them what must the function be. So once you have trying to extract f of x plus h minus f of x all over h, they're trying to get us to go backwards and figure out what is the function, what is f of x, and what is the number at which we're actually, what is our x value. So is there anybody that thinks they can tell me what the function is? Not. Wait, say that again. No, because you're missing the two parts. This is your f of x plus h part minus your f of x. But two things have happened here. We've plugged in, well, and it's not an h here, it's the change of x, but for just to simplify things. We've already plugged in the x plus h and then plugged in the x value at which we are looking for the derivative. So here's your x plus h. So that's your c value. That's the location at which you're looking for the slope, is at -2. This is f prime at -2. We're looking for the slope of the function at -2. What is the function, then, that I plugged x plus h into? Nathan? X cubed. So the function is x cubed, and once I kind of do it forwards, I think it'll be a little bit clearer. So if I was looking for the derivative of this function, f prime of x would equal the limit as change of x approaches 0 of f of x plus change in x. So if I'm doing f of x plus change in x, I'm plugging in x plus change in x minus f of x, which would just be minus x cubed, all over change in x. That would be my derivative formula. But this is specifically asking us to find the derivative at, I'm just replacing my x with negative 2, which is why, give me 1 second, Stephanie, which is why that is a negative 2. Minus, and when I plug negative 2 in here and cube it, that's going to be minus negative 8, yes? Which turns it to a plus 8, all over change in x. So the derivative specifically at negative 2 now then comes from plugging in a negative 2 for all those x's, which is the expression we have over there. Stephanie. So what's really tricky about this one is that if it was this alone, and they just said, what's x cubed, we could, or what's the function, we could kind of, I think, we could realize that it's x cubed, because here's your f of x plus h minus your f of x all over h. But they did two things. They did the limit rule, and they then specifically were looking for the limit at a certain number, in which case all your x's got replaced with a negative 2, so it kind of hid this from us. That's a tricky one, a different way of presenting it. We've seen some multiple choices on this kind of idea of thinking backwards, but not one that also plugged in a number at which we were looking for the derivative. So this was is a little bit more complex. Any questions on that? Okay. If we jump to the next one, it wants us to identify a function and sketch a function that has these characteristics. So they're giving us the function value at 0. They're giving us the derivative or the slope at 0. They're telling us that the slope is negative for any x value less than 0. And on this one, they're telling us that the slope is positive for any x value greater than 0. Giving us features that we then need to sketch a graph for. So the easiest place to start is by plotting a point that we know is on the function 0, 4. And then they're telling us that the slope right there at 0 has to be 0. So this has got to be either the bottom of a parabola or the top of a parabola, something that will have a 0 at that location, a 0 slope. I don't know if it's opening up or opening down yet, but this will tell me. The derivative is negative, meaning the slope is negative anytime we're less than 0, which is on this side of the graph. When x's are less than 0, your slope should be negative. So is this slope negative, or is this slope negative? Is it going to be a parabola that opens up or a parabola that opens down? If it opens down, that's a positive slope. We want our slope to be negative. So we like this one, because our slope coming in from the left is coming downward. So for all of those x values to the left of 0, we have a slope that is negative, coming down into that point. Then right at that point, it's a slope of 0. And then after that point, for all of these x values that are positive, your derivative or your slope needs to become positive. So it actually turned around and did that. Then that derivative at 0 would have been undefined. If it was coming to a point as opposed to a smooth curve, they would have needed to say that the f prime at 0 does not exist. That would have led me to bring that to a point. Does that make sense? It's a great question. Jalen. if it did this, that's not a positive slope, that's decreasing. That's a negative slope. That's going down. I could, and so this is the end of the problem. And if they wanted us to make up a function, we could just say x squared plus 4. That's just a parabola parent graph that's been shifted up 4. But they could say, they could make our derivative negative, like if, and you don't need to write this down, just think about it, because I don't want you to confuse the problem that this was. But for all x is greater than 0, if they tell us that our derivative continues to be negative, that means our slope continues to be negative, and the graph is decreasing then on that side as well. So that would kind of be something like this. And it wouldn't have turned into a positive slope. It would have been decreasing the whole time, right? A slope that's negative means the graph is decreasing. So if you want to interpret the negative slope here as a decreasing graph, you can do that. Okay? So they get a little tricky, these graphing ones. And there'll be bits and pieces. There's not a whole ton of your homework that's on this kind of thing. Eventually, I will spend an entire day looking at these graphs, though. Yeah. It just says identify a function. Yeah, yes. I've just kept it as simple as possible. Yeah, there's several functions that would do that specifically, but the look of them would all have to be a parabola opening up with a vertex at 0, 4. Okay, I didn't write down this next example. I just wrote down that I wanted to go to page 132, number 54. So, what did I like about this one? Okay. All right. So, this shape is giving us the graph of the derivative. This is not the original function g. This is already the graph of the derivative. Okay? So, g prime of 0 is what? -3. Yes? That means on our original graph, the slope at 0 is a slope of -3. Do we follow that? G prime of 3 is what value? 0. That means on our original graph, at 3, it has a slope of 0. What can you conclude about the graph of g knowing that g prime of 1 is -8/3? So at 1, our slope is -8/3. So on our original graph, at 1, it's decreasing. That's what that tells us. If it has a negative slope at 1, that means on our original graph, it's decreasing. What can you conclude about the graph of g knowing that at -4, we have a positive slope, right? Here's g of -4. It's up here in the positive. So this is where this gets confusing. Because on this graph, at -4, this particular graph is decreasing, the one that we're looking at. But the original graph, the g graph, this is telling us that at -4, our g graph has a slope of 7/3. It's positive. So on our original graph, at -4, we have a positive slope, which means on our original graph, it's increasing at -4. Okay, this will take a while. Are there any questions on that? It's just the magnitude of our positive slope is becoming less and less. So your original graph is increasing very fast here because it's got a high positive slope. And it's still increasing here, it's just not increasing as quickly because it's only a +2 slope. And then maybe like right before it hits the 0, it's still increasing, but the y-coordinate here is like 1/8, let's say. So your original graph is still increasing with a positive slope of 1/8, but not nearly as quickly as it used to be increasing. So the rate of your increase is slowing until you get right here at -3. At -3, we're showing a slope of 0. So on your g function, if you were to sketch it, at -3, it's probably the vertex of some sort of turnaround point. Because as soon as you get past -3, we're into the negatives. So on your g graph that you're not looking at right now, but we should be able to start to envision, is that right after -3, the slope being negative is going to show on the g graph as it started to decrease. So it was a positive slope going into -3 and a negative slope coming out of -3, which means it was some sort of turnaround point. Positive slope going in, negative slope coming out. E asks if g of 6 minus g of 4 is positive or negative. Oh dear word. At 6, the slope is very, very positive. Oh, I gotta go up to the board, I think. Let's sketch something. I'm gonna sketch a potential g graph. Okay, there's g prime. So g prime of 0 is -3. So at 0 on my green graph, I have to have a slope at -3. So a pretty steep negative slope. I don't really know where it would be. It could go here, it could go here. I know nothing about the location of this graph. I'm just going to get info on the shape of it. So since the slope of 0 is -3, on my g graph, I'm drawing a very negative slope at 0. At 3, a prime of 3, I'm at 0. So my slope of my green graph at 3 is 0. So right around at 3, I need to have a 0 slope. I need to like balance out. Yes? What did you conclude about the graph of g1 that g prime of 1 is -3? So at 1, I should have a negative slope. I do. Right? And it's not as negative as it used to be. Here it was -3. Here now it's only -1/3. It's becoming not as steep, still negative. That's because we're approaching kind of a vertex of some sort. Follow? Okay? Key features are really these zeros. Because if your slope graph is showing a 0, then that equates to like a vertex of some sort on your original graph. The same thing's going to be true over here. Okay? That's a 0 there. So we have a negative slope right up to there, but then there's a 0 there. Right? G prime of -3 equals 0, which means my slope at -3 needs to be a 0 slope. Prior to -3, my slope is always positive. So prior to this location, my slope needs to be increasing and positive going into that. Follow? And then what's happening over here? Once I get to a 0 slope, everywhere after this, my slope is in a positive. So since my g prime and my slope is in a positive, my actual graph needs to increase it. And that's the look of it. Now this could be split up or down or anywhere. I don't know anything about really the location of it, but I know that my slopes are doing that sort of adjustment. So zeros on your derivative graph are going to equate with kind of vertexes of some sort on your actual graph. And being in the positive region on your derivative graph is going to equate to increasing on your original graph. Being in the negative on your derivative graph means my slope should be negative from here to here. So it's decreasing from there to there. And again, prior to this, correct. And what you guys, and when we do the shortcut, we'll point out more of these features that those of you that know the shortcut know that if something has a degree of 3, its derivative is then going to have a degree of 2. And this is a perfect example of this. If my original graph is a degree of 3, then the derivative is just a degree of 2 of the quadratic. And then, kind of goes down here. We'll talk more about that. So all of this to get to is g of 6 minus g of 4 positive or negative? This is sort of tough to tell. G of 6 is a bigger number than g of 4. Now I can see that because we were increasing from 4 to 6, I know that g of 6 has to be a bigger number than g of 4, so I would say it's positive. The explanation would be in the fact that I know it's increasing on that interval, and therefore the second point, g of 6, has a higher value than g of 4, and then you get a positive answer. Is it possible to find g of 2? No, it's not. All I know at 2 is that it has a slope of 0, but like I said, this could be shifted up or down. I don't really know its location. So to actually come up with a point for g of 2, I couldn't do that. I know what the slope is at 2, but I don't know where the location of the graph is at 2. Yes? Okay, that's just an introduction. That's heavy for everybody. So we have to start something. So here we are. I'm sure we'll have questions on those on the homework when we do graph works, but I wanted to discuss. We flip to the back. Any questions? Okay. All right. So this is brand new to us. There's another way of finding the derivative, not yet the shortcut, but this alternate form of the derivative. And what it does is rather than finding the derivative formula, it jumps right to evaluating what is the derivative at a certain location. So if I had a specific point on a curve in mind, and I wanted to find the derivative at that value, I can find the limit as x is approaching that number. So you have your 2 points, c, f of c. This is where I want to know what the slope is at this point. And then I have a second point, x, f of x. And essentially, we're thinking about the secant line connecting these two, and what is the slope of that line going to approach as I slide x closer to c. Okay? So your limit now is as your x coordinate gets closer and closer to c. So you're sliding this point along. What is the limit of, again, the slope formula? y2 minus y1 over x2 minus x1. F of x minus f of c all over x minus c. It doesn't give you the derivative equation that we've been getting, that we're allowed to then use to find the slope at any given point. It gives us specifically the derivative at one and only one location. So if you already know where you're looking for the derivative at, this is just a faster way, but it will not give you the derivative formula that we've been used to getting. So like, if we look at this first one, if we wanted to know what is the slope of this function specifically at 4, we would just do the alternative form. So f prime of 4, the slope of this function at 4, is going to be the limit as x approaches 4 of f of x, which is our 3 over x, minus f of c now. If I plug in c of 4, what's f of 4? 3/4 all over x minus 4. And again, there's going to be some manipulation involved. So I'm going to multiply by the least common denominator of 4x. When I distribute that through, that's going to make 12 minus 3x. Did I do that right? Over 4x, x minus 4. And I can factor that numerator, right? I can take a 3 out of it. So it would be 4 minus x instead. And then the 4 minus x and x minus 4 can cancel to make a -1. So I'll just throw a negative in front of that 3. And now I can directly evaluate. I can actually plug in a 4 for the x, and I'll get -3 over 4 times 4 is 16. So now that we've seen this problem through, this alternative form isn't giving us a derivative formula to use for any general location we might be interested in. It's specifically, because we used the 4 in there, it is specifically just immediately giving us the slope at 4. So not finding the derivative equation and then later on using it to find f prime of 4, it's getting us right to that numerical answer. Okay? Let's look at this one. This wants the derivative g prime at -3. So this will be the limit as x approaches -3 of f of x, which is just x plus 3 to the 1/3 power, minus f of c. So what is f of c? If I plug in -3, I get -3 plus 3, which is 0. What's 0 to the 1/3 power? 0, right? All over x minus -3, which will be x plus 3. And so now I'm just finding the limit, and I still need to manipulate this. I'm just going to get rid of that 0. So what do you do to manipulate something like this? That doesn't keep the same value. If you cube a numerator and cube a denominator, right? Think about numerically, 1/2. If you cube the numerator, cube the denominator, you change the value. What do you think? Rationalize the numerator by doing what? Say it again. That would rationalize a square root, but a cubed root, if you multiplied by another cubed root, that's not gonna, you want to fill the, yeah, because it's 1/3, you would need to multiply by x plus 3 to the 2/3 power, yes? Or, these have common basis. So if you were to follow your exponent rules, when you divide these, you keep the same base, and what's 1/3 minus 1? -2/3. And then if you got rid of that negative exponent, it would be 1 over x plus 3 to the 2/3 power. Now, unfortunately, this is one of those limit type problems that manipulation's not going to get rid of anything for us. So we have to think about this in a different way. If you are approaching -3, and if you want to, you could turn this back to, like, if you want to, if you're more comfortable with it, you could turn this back to the cubed root of x plus 3 squared. It's up to you. But if we're plugging in something really, really, really close to -3, what is this number going to be? Teeny tiny, right? And then you're going to square a teeny tiny number, which is still going to be pretty teeny tiny. Even teeny tinier, actually, right? A small number times a really small number makes it even smaller. And then you're taking the cubed root of it, which makes it even smaller. So 1 divided this by a number that keeps getting smaller and smaller is what? Infinity. 1 divided by numbers that get smaller and smaller and smaller and smaller is infinity. So then let's think back about this. What is the derivative of this function at -3? Infinity? What do you think that means? Okay, let's look at the function. I like where your head's at, Jalen. Sounds like a good guess. Does anybody have any other guess as to what that might mean? If your derivative at a location is infinity? Maybe. The point is, we know that having a limit of infinity is a does not exist limit, right? It's just a more specific version of does not exist. So essentially, the derivative at -3 supposedly doesn't exist. And let's look at it and see why. So x plus 3 to the 1/3 power. And let's go from -6 to 0 so that the location at -3 is right in the middle of that. Okay, so what happens is, it's kind of like a cube graph, but it's turned sideways because it's a cubed root graph. And this is increasing, 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 and then it almost for that just that instantaneous moment at -3, it's like a vertical line. Yes? And then becomes a positive slope again and kind of evens out. But if that little instantaneous moment is a vertical line, the slope of a vertical line does not exist. Yes? So that's why that happens, and you could just say equals does not exist. I don't think this is the easiest way of doing a derivative. I will be honest with you. This alternative form of the derivative, it's fine for this, but it's much more limiting. It only gives you the derivative at that one and only one location. If you ever then had to say, okay, well then what's the derivative at 5? You'd have to redo that whole process again. What's the derivative at 6? You'd have to redo that whole process again. I do like the f of x plus h method because it gives you a formula. F prime of x equals, and it gives you a formula. So if you wanted to find the slope at 4, you would just plug 4 into that. If you wanted to find the slope at 5, you would plug 5 into that. It's more conducive to all these different scenarios. But at the end of the day, this is something you should know, how to use the alternative form of the derivative. And the equation is similar but quite different. Like, it's not your limit as anything is approaching 0 anymore. It's not an h that's approaching 0. It's the actual x value sliding closer to the point of interest. And those are the big differences. So when the directions say on your homework to use the alternative form of the derivative, please use it and practice it. Don't find the old derivative just because you're more comfortable with that. Get out of your comfort zone. Try this weird and new thing. It'll probably bring up a whole host of questions that we can clarify and learn from. And then once we get past all this, you can do whatever you want. But let's practice what the skill is that we're learning today.